Hello, class. Welcome back. Today is lecture 10. We are talking about solving second order linear homogeneous equations with constant coefficients. So I know we're going to do nth order, is what I said originally, but today we'll also see why we pretty much just stop at second order, but we could do more. Okay, and it has to do more with algebra than it has to do with differential equations. Okay, so let's get to it. So next, we learn to solve things like this. So the title right now is a lie because I'm saying second order, but here I'm writing nth order, but that's okay. As I said, we'll see why we just stick to second order once we get to it. Okay, so we learned about this linear dependence, independent stuff to help us deal with this, and now is the payoff. So first we're going to start simple. So the way we got to this in the first place was starting simple, making things simpler. Now we're going to go even simpler than that. Let's just worry about first order. So what would a first order equation of this kind look like? It would look like just the first derivative and only one constant coefficient on the next term, which would be just the function and still equal to 0. So this is a first order of these kind. So of course we could solve this using the fact that it's separable and linear, the old kind of linear, but we want to think about it a little bit differently in a way that'll help us solve the bigger ones. Okay, so we're going to think about it like this. So because it's a first order, last time we learned that that means that there's exactly one linearly independent solution, because if it's nth order, then there's n. Right now, n is 1. So there's one linearly independent solution to this differential equation. We're going to figure out what it is. I'm going to call it y1 of x. So I don't know what it is yet, but I know it's a solution. So then it has to exist. It's a solution. So if I plug it in, y1 prime plus a0 y1, then I will get 0. So let's think about this a bit more. What is this thing? It looks actually very familiar to yesterday's things. So the left side is a linear combination of two functions. What are the two functions? Well, of y1, this mystery function that I don't know yet, that I'm trying to figure out, and also its own derivative. So if I take its derivative, I get a new function. So the left side is a linear combination of these two. But then what's the right side? What's the significance of the right side? Well, it's 0. So it's a linear combination equaling 0. And the coefficients are not all 0. In fact, there's a 1, secretly a 1 here that you never write. So that's definitely not 0. So the coefficients are not all 0. So what does that mean? According to last time, what does it mean if you can build 0 out of two functions and without using 0 as the coefficients? That means that they are linearly dependent. So this is the way we want to think about y1 and its derivative, because that's a very useful relationship, especially when there's only two functions. So if there's only two functions, being linearly dependent means that they're multiples of each other. And we only know, you might already know, one function with this property that it's a multiple of its own derivative. So it's definitely not going to be something like derivative. It's not going to be something like x cubed or x to the fifth, because whenever you take the derivative of those, you get a new function type that's not dependent on the previous one because the power changes. So what we're looking for here is that y1 of x has got to be an exponential function. Because when you take the derivative of an exponential function, you get a multiple, because you just bring that r down with the chain rule, of the original function. So it's just a multiple of the original. Great. So what we know now is that our solution, y1, has to look like this, but we don't know what r is yet. Which r will this work for? So now let's plug it in to see what r must be. So remember the differential equation was y prime plus a0y equals 0. So now I'm plugging in my y1, e to the rx times r plus a0 times e to the rx equals 0 to solve for r. So here we can factor out e to the rx. And because this is an exponential function, we know that this is never 0. So in order for the multiplication of two things to be 0, in order to have that happen, we need one of them to be 0. So we need this to be 0 instead. So I can solve for r now. So r will be negative a0. So whatever that constant is here, that's going to tell you r. So then y equals e to the negative a0x is the one linearly independent solution. But then the general solution, remember, is a general linear combination of all the linearly independent solutions. There's just one. So then the general solution is a constant times that function. And that's it. So this will be the solution to any first order. So we already could have done that with separable equations or integrating factor, actually, and you would have got the same thing. But we want to think about it just for now like this. Okay, so very quickly, if I want to solve something like this now, the general solution is, well, I know that a0 is negative 3, so it's y equals ce to the negative 3x. ce to the 3x. You could verify if you use the other techniques we've learned that you will get the same answer. Okay, good. So now we're going to move on to second order, and we're going to use the same logic to figure it out. AKA, we're going to be solving something like this now. So we have two constants, a1 and a0, and we want to think about it in the same way, which is, notice that the left side is a linear combination of three functions equaling 0 again. So they must be linearly dependent because the coefficients are not all 0. So do I know a function whose derivative and second derivative are both the same type of thing as it? I do. It's e to the x again, e to the something x. Okay, so y1 of x equals e to the rx has this property, which is if I take its derivatives, I do get 3 linearly dependent functions because these are all just multiples of each other by different amounts. And then what I want to do is I want to plug these back in and see what exactly R has to be for it to equal 0. So that's what we're going to do next, just like before. Okay, so then we'll determine R by plugging this in. So y double prime, I'll rewrite it here, plus a1 y prime plus a0 y equals 0. So my y double prime is r squared e to the rx plus a1 re to the rx plus a0 e to the rx. I want this to be 0. I can factor out my e to the rx again and safely know that that will never be 0. So this is never 0. So to make this be 0, to determine R, I can set the other piece equal to 0. And I can solve for R in terms of the constant coefficients A1 and A0 that would be predetermined in the problem already. And this might look very familiar to you, just with different letters, this thing here. This is actually a quadratic. You could think of this piece on the left here as being a quadratic polynomial, meaning second power polynomial, but in terms of R. So normally you're used to seeing things like it would be like x squared plus some number x plus some other number equals 0. And how would you solve something like this? What's the magic formula that solves this? You would use the quadratic formula to solve for x. Well, it's just a different letter. Now we're solving for R, but we can do the same thing. So we can solve for R the same way. Or if it's easy, if it happens to be easy, you can actually just factor this thing to figure it out instead, to figure out R. Okay. But I'll remind you of the quadratic formula. So R will be negative b, so negative whatever that number is, plus or minus the square root of b squared minus 4 times a, the number in front of the first term, which is a 1, times c, which is the last term, over 2 times the first term. So what we've done is that we found that that there are two solutions. Y1 equals e to the rx. These are both solutions where r equals either the plus from the quadratic formula or where it's the minus part. So what we've done is we've turned solving this differential equation problem into just solving an algebra problem, basically just using the quadratic formula. And then we get two solutions. Now there are some subtleties that we're gonna have to think about in a second, but for now, that's not so bad. So what are the subtleties? Well, it has to do with this piece of the quadratic formula. So several things could happen, and that's what we'll be thinking about next. From algebra, you might remember that there are 3 situations. Okay, but the point is we found R, but we got to now investigate specifically what happens. So So for that, I'll do examples for each case just to see what's going on. It'll make it a lot easier. All right, so there's 3 cases from algebra. This is what we know. There are 3 cases, 3 things that could happen. Case 1 is the easiest case, which is that the 2 values of R that you get are just 2 different or distinct real numbers, like 7 and 12 or something like that. Just 2 numbers, nice and easy. So let's do an example where that happens just to see. So solve y double prime plus 6y prime plus 5y equals 0, something like this. So we're going to do all this stuff that I just talked about. So we're thinking about, I'm just going to call it y because I don't want to keep using y1 and y2, but secretly there's like 2 different functions I'm trying depending on r. Okay, so consider e to the rx. Y prime would be r e to the rx. Double prime would be r squared e to the rx. And then I'm plugging these in. And this part will always be the same, except for these different letters, these different numbers, so 6 and 5 this time. So I plug these in. E to the rx will still factor out, but now I'll get this quadratic equation here that I'm going to be setting equal to 0 to solve for r. So now if I didn't know how to solve this, if I didn't know how to factor it, luckily I do, then I could use the quadratic formula. But because it's a nice factorable quadratic, it becomes r plus 5 times r plus 1. I don't have to do that. So I get 2 values of r. And if you use the quadratic formula, you'll get the same 2 values of r. So then this tells us that y1 of x is, so one solution is e to the negative 5x, and another solution is e to the negative x. So all I'm doing is putting in r for the function here to get 2 solutions, for 2 different values of r. But one thing to notice is not only are they 2 solutions, they are 2 linearly independent. So you can check that they're linearly independent solutions, but that's the best part, is that they are linearly independent, because that tells us the general solution, because it's second order. So since the DE was second order, there's only going to be 2. We know there's only 2. So I'm not missing any. And I have 2, so I have as many as there are supposed to be. So the general solution, I can say for sure, is just the general linear combination of these 2. So C1 e to the negative 5x plus C2 e to the negative x. That's it. That solves for the general solution of the differential equation. So that's the easiest version. If r is 2, there are 2 values of r, then you just go through it like that. In fact, you can skip lots of steps and make it much quicker, which we'll do when we get more practice. Okay, but case 2, so then it becomes a little bit more annoying with different cases. So case 2 is, what about if you have the same 2 values of r? So the 2 values of r are the same. So this can also happen depending on what the polynomial is, the quadratic polynomial is. So let's see an example where this happens. Okay, so now what we're going to do is we're going to speed it up a bit. So we write something called, because we already know we're in the right situation, we write something called the characteristic equation for the DE to solve it. And some people call it the auxiliary equation. If you look in the book, that's what it says. But what is it going to be? It's just that equation you get from doing that whole process. And that this is what it is in that case. So notice the correspondence between these terms. That's really what's going on. Is you just look at your differential equation and you rewrite it with r's and the same numbers, basically. So, and where does this come from? It comes from the same process as before, meaning you do this, but it turns out to always work the same every time. And then you plug these in, and then you take out the e to the rx. Works the same every time. So we just skip to writing the equation that you get at the end, which is called the characteristic equation. Okay, so then we solve this thing with algebra, and it turns out to factor into r plus 3, r plus 3. So that means I only get -3 as my r. And the quadratic formula, if you use it, you'll only get -3 as well, because you get a plus or minus 0. That's what's going to happen in the quadratic formula. So what does this mean? Well, it means I know that this is a solution. It's linearly independent with itself because there's no second one yet, but I'll still say linearly independent. Actually, it's just one solution. But what about the other one? You can't just have the same one twice, because then they're not linearly independent. If they're the same thing, they're definitely not linearly independent. So y2 of x being just the same thing doesn't work. So I can't just use r equals -3 twice like this, because then I don't get two linearly independent solutions. So instead, the second equation, the second solution, you can determine it using this other method that we've skipped. It's just too much work for a little payoff, so we're going to skip it. But it's called reduction of order. You can go look it up if you want. So instead, we just use some math magic to know that if you have a repeated root, a repeated solution, that the second one is just going to be the same, except you multiply it by an x. So you just take the first, multiply by x, and that'll get you a second one. And these are linearly independent. These two things are linearly independent. They are not constant multiples of each other. And you can check that this is a solution if you want. But it is. So the fact that it is a solution is actually good enough, because we know there's only going to be two. So even though I just guessed it, so it's unsatisfying, that's fine, because now that I know it is it, I know the general solution. So then the general solution is my two solutions, linear combination of them in general, and that's it. So again, we're just going to use a result. We're not going to show where this one came from. We're just going to call it math magic, but you can. It's called reduction of order. If you want to go look it up, you can figure out that other solution. Okay, but we got a lot to do, so we're going to be skipping lots of things like that and just using them. All right, case 3. So now the two values of r are complex conjugates. Very scary sounding. So in the quadratic formula, if you have a negative in the square root, this can happen. Your two answers will be complex numbers, and they will be of the form a number plus b times I, and the same two numbers, but with a minus. And that's what conjugates mean. It means that they're the same, but you have one that's a plus and one that's a minus. Okay, so let's see. So this happens. When this happens, it means you are definitely going to use the quadratic formula. Well, maybe not definitely, but probably. And then you'll see how this occurs. Okay, so let's solve y double prime plus 4y prime plus 13 equals 0. So the characteristic equation is then r squared plus 4r plus 13 equals 0. I'm going to have to use the quadratic formula because I can't factor that easily. So negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 13 over 2 times 1. R equals negative 4 plus or minus square root. Okay, this is 16, that's 52. 16 minus 52 is negative 36. So now we see where the complex numbers come in because I get a square root of a negative there. So that becomes plus or minus 6i over 2. I can cancel the 2 with the 4 and the 6 to get negative 2 plus or minus 3i. So my two r's are negative 2 plus 3i, negative 2 minus 3i. So they're called conjugates again because of the plus and the minus. And so my two values of r are these. So now I'll plug them in. Call them r1 and r2. So these give my two linearly independent solutions, e to the negative 2 plus 3i and e to the negative 2 minus 3i. Oh, times x, of course. Each of them. Great. So you might think this is it, but unfortunately it's not. We can actually simplify a lot, and we can actually get rid of the imaginary numbers. That's what we're going to want to do next. So then the general solution for this situation, it looks complicated at first, but it's going to simplify quite a lot. So C1 e to the negative 2 plus 3i x plus C2 e to the negative 2 minus 3i x. So you might notice that if I distribute the x through and I write it like with the bases separate, then I can do some simplification here. So I can factor out this e to the negative 2x. And now I'm going to invoke some more math magic. Meaning I'm going to use something about complex numbers that you may have not learned, but you can look up if you would like to learn about it. So this is coming from something called Euler's formula. If you want to look it up. Formula. So it says that e to the I times an angle equals cosine of that angle plus I sine of that angle. So I'm just using this formula. You can look it up if you want and try to work it out, but I'm not going to hold it to you. So I'm just going to invoke this and tell you what this reduces to. So it becomes C1 cosine of 3x, C2 sine of 3x. So nice thing about this is all the i's have vanished, so there are no more imaginary numbers in our solution. So what you should notice is these numbers, though. This negative 2 And these threes, that's the pattern we're looking for. That comes from here. Okay, so let's go ahead and summarize the technique for all three cases so that you have something just that you can always use. So a second order, a differential equation, it looks like this. What's going on? Well, it has solutions that correspond to solutions algebraically of the characteristic equation. So if you solve this with algebra, then you automatically solve the differential equation. And that's basically why algebra is so nice, is because it's much easier. So if you can turn your problems into algebra problems, then you can do them. And that's the point of this technique, is turning our situation into an algebra situation that we know how to better deal with. Okay, so then this is solved either by factoring or the quadratic formula, which I'll just call algebra, solved with algebra. And then the correspondence breaks into three cases. One, first case was if there's two values of R, two distinct real values of R. So if you call them R1 and R2, then your solution looks like C1e to the first one, x, plus C2e to the second one, x. So you find your two values of R, stick them in there, and then you're done. That's the answer. If there's one repeated value of R, so you would just call it, you can still call it R1 if you want to use labels. Then what's the general solution? You stick that in, but then on the next one, you multiply it by an x. And then the R1 is the same on both. There's only one value of R being repeated. And then lastly, there's two complex values of R. Well, they're always going to come in a pair that looks like this. So in that situation, your solution is always going to be e to the ax, so whatever the real part is what they call it, the real number part, times C1 cosine of bx, so that's where the imaginary parts come in, plus C2 sine of bx. So you don't have to work these three things out every single time. This is the general format. Okay, so there, you can see it all at once. And then very quickly, just to trick you at the very last second, people use lambda instead of R typically. Whoops, we used the different letter the whole time. Why did I do that? I don't know. It just looks nicer when you're teaching it, but once you know it, then you're ready to bring in fancy Greek letters. And then the last thing I want to say is this technique applies to higher order things. So for example, y fifth prime plus 3y double prime plus 2y prime plus, I don't know, y equals 0. It has a characteristic equation. So now I'll switch to lambdas at the last second. Lambda to the fifth plus 3 lambda squared plus 2 lambda plus 1 equals 0. But what's the problem is that these are much harder to like factor or use the quadratic formula or something. Once you reduce its degree, it's just much harder to find the roots, hard to find the solutions. Sometimes it's impossible without help. So that just means that solving this is also very hard because I can't do the algebra part of it. So that's why we typically stick to degree 2, but the same rules apply for the higher ones. Okay, so that's it for today. I will see you next time.